So now we move it to a chapter on turbomachinery. This really, turbomachinery is a general term. It's for pumps, it's for compressors, it's for turbines. It's rotating machinery that has fluid going through it. It could be liquids, it could be gases. It's one of my favorite sections of the textbook. I always try hard to get to this section and make sure and cover it. I think it's very practical. When you get out, they may not quiz you a lot about what are the derivatives in the Navier-Stokes equation and need to apply something like that in your first day first day on the job or first week on the job. But you often are confronted with practical problems dealing with pumps and compressors and turbomachinery. So fans, blowers, compressors, all of these devices. And what we have are some devices that consume shaft power, and some devices produce shaft power. And so what is the difference between hydraulic turbine? Well, what's a hydraulic turbine do? It's like in a hydroelectric generating plant where they had built a dam to stockpile water, get a high elevation, large change in pressure from the bottom of the dam to the discharge on the other side, and they can put a turbine in there and the water doesn't change phase, and you can generate a lot of power. And quite a bit of electric power is generated in the United States using hydraulic turbines. Steam turbines, see that in power plants, gas turbines and power plants as well. And then also we want to put the device, whether it's a pump or a blower, compressor. Often I'm going to focus a lot on pumps, because if you understand pumps, it goes a long way in understanding a turbomachinery. We put them in a system, connected with the system, and you can talk about different losses and how the pump behaves coupled or placed into the system, or a number of pumps in series or a number of pumps in parallel put into a piping network system. Well, here's a picture of a centrifugal pump. So you can see the electric motor right here. What's this line running over to there? That's the power. That's electric conduit. Okay. Now out, they have this device right here. What is that device? It's a shroud. What's a shroud do? It just protects you. It's going to have a rotating shaft right inside there that goes from the electric motor over to this pump on this side. So this is all the electric motor, and there's a shaft feeding to pump. Okay. There's some support structure and bearings to the pump right here, but often if you have an exposed rotating shaft, enclose it or shroud it, but protect it. Number one, when you were little and you saw something glowing red hot in the kitchen, what did you just want to do with your little fingers? You wanted to touch it. Whenever you go into around rotating machinery, you see a beautiful shaft just humming along. I don't know what it is, but what does your little finger want to do? It wants to touch it. Don't. It's extremely dangerous. And anything gets caught. Hair, a piece of cloth, a tie, you're in big trouble. So it's very important to shroud those rotating shafts, and know that just like when you were little, you wanted to touch something red hot, to glow red. You didn't know it was hot. You just wanted to touch it. We still want to touch things that rotate. I was talking to somebody and he lost half of his thumb because he just was working with a piece of machinery in the back of a tractor and wanted to just touch that rotating shaft. And it just took that split second. He wasn't even thinking. It just moved in there and just touched it for a second. For some odd reason, boom. So there's a lot of accidents that happen that way. Okay, so now we have the pump, and the pump, this is just a support for the structure. Right here is the heart of the pump, and we have two pipes. This is a pipe right here, and this is a pipe right here. Fluid's got to come in one pipe and out the other pipe. So which pipe is the fluid coming into the pump at, and which direction is the fluid going out? Just by looking at the pipes. connected to it. Which one is the inlet pipe and which one's the outlet pipe? Which one is this one right here? I'm waiting for the correct answer. It's the inlet pipe. It's the inlet. Inlet. See, you don't know much about this, so we're learning together, right? And this over here is the outlet pipe. Now, you really can't tell that much, like, why is that the inlet, why is that the outlet? Maybe I should have taken this photo from that direction. But here's something that's around the pump, essentially. And right in here, a pipe is connected to it. That pipe is this inlet pipe. It comes in the middle, right here. Okay, and then over on the back side going up is the outlet pipe. Does that perspective help a little bit? And it's only experience and knowing why or how these machines work that you can tell, oh, that's obviously the inlet and that's obviously the outlet. Because that shaft coming in here is making something rotate. And something rotate is a section like this that has some veins in it. Am I going to draw this right? Depending, no, draw it this way. There, some veins in it. And the fluid comes in, turns at 90 degrees, is caught by those veins and is slapped around in there and thrown out, and it's going to come off the tips of these that's rotating in this direction as I sketched it, and then thrown up and out the outlet pipe. That's the way a pump works. We'll spend some more time looking at some illustrations, some better illustrations, but that's the way the pump works. It's really easy to analyze it using the concepts of not linear momentum, but angular momentum. Angular momentum. I think we already covered the Euler equation, didn't we, in that angular momentum chapter? We'll review it, not today, but next time. Well, there's a couple different types of pumps. So you'll see the classification of radial, mixed flow, and axial flow. I would like to just spend a lot of time talking about the radial flow pipe, or pump. But here is a description, just some illustrations. You put this device into a tube, and if it's rotating, the shaft making it rotate, it'll, just like a propeller, grab the fluid and be motivating its flow down the axis of the pipe, or that axis that the shaft is coming in to feed it. So this will be an axial flow. You will see some of these pumps around. Plenty of them around. I mean, they're all over. They're good for high flow rate. They're good for low pressure. They don't really generate a high pressure. That's an axial. Then we have mixed and radial. Here is more of the traditional radial. You can find a lot of these. I should have grabbed a couple of. If you walk through mechanical rooms, every now and then you'll see one old one laying on the side. They switched it out or replaced it. I should snag one and bring it in for show and tell. Pass it around. It's a little heavy and a little, junky if it's been in service and it's trash. But the water would come in, the liquid would come into the eye region. This whole thing would be rotating, and what would happen is the veins are typically angled, and they have this side and the back side, front side, so it goes through this passageway that has the veins, and then it's thrown out, slapped out, spit out, whatever you want to call it, out the other larger radius R. So the inlet in the eye and the outlet out at the larger radius of the impeller section. Mixed flow. Well, the blades are not just more one-dimensional; they're more two, three-dimensional. So the flow comes in, it's caught, but it's also thrown out radially. So it's not just axial; it's kind of a mixed axial radial flow. And you'll see some of those. These are a little more tricky to make, maybe a little more costly in the manufacturing, but maybe that cost difference has gone down over the years because of the advancement in CNC They can machine things that are pretty complicated. But this is radial flow is probably the workhorse of the pumps that you see out there. So here's another illustration. You have a suction section, that's the inlet, and the fluid comes into an I region. Here they're showing you the impeller goes all the way to the center, but it doesn't have to be. Often that center I region's hollow, and the vanes start at a given radius R1. So the water would turn 90 degrees and then go out into the section that has the impellers that is rotating. The impellers go out to radius R2, and often they can be just straight sections out, or they could have curvature to them. A lot of them have curvature to them and thickness to them as well. But you can see pumps that are really just like this. Anybody taking a look at a water pump on an automobile? What do they look like? Typically really cheap. Flat blades sticking out. You can get water pumps real cheap. You have a friend that works on cars. When they tear one apart, take a look at it. Okay. Cheap water pumps for like things with aquariums or other things. Go look at those. Easy. You can buy them. They're cheap. Take them apart. They're almost always little radial sticking out. Easy to manufacture. The more expensive, the things that have to consume a lot of energy and run 24/7, those they spend a little more time to make it more efficient. And they'll have curvature to the impeller blades. Okay, and then so it rotates, and then it's caught in an increasingly large area until it's discharged. It's a what they call a volute region. It's catching it and changing the direction such that it comes out one-dimensional in the outlet or discharge. Here's another illustration. This one's out of our textbook. So let me go through this. You have that volute region. It's growing in size. They've exaggerated here till you get to the discharge. There's a little cut right there. Okay. So that's picking up where we had this impellers. Here they're showing them with some angle, some curvature on the impellers. And they're showing you a hollow inlet I region, the I region, where the water would come in, turn, and then go into the impeller section, and then be spit out, kicked out, slapped out off of the tips into the volute region, and then that's collected up. Okay, the impellers sometimes will help navigate the turn, and so this is an illustration where the impellers start and are catching it more like a mixed flow, but it's got some different height or width. Let's say, what is this? B, a parameter B1 and B2. So that's a height of the section on the inlet. B1 is different than the height on this outlet B2. You see the parameter B1, B2? What, do you understand it? And so what it's doing is it's helping it turn. You can tell there's some curvature here, so it's more of a mixed radial axial type pump. It's a mixed flow. So you have that rotating shaft. It's spinning, especially the impeller section. The impeller section's intaking the fluid, discharging the fluid. It's going to be changing the angular momentum flow rate of the fluid, and you can relate that to the torque in the shaft with Euler's equation, angular momentum. And if you have a torque of the shaft and the shaft is rotating at a specific speed, omega, you have power. What is the power of that rotating shaft having a torque tau and a speed omega? It's a product. It's the product of the torque and the shaft. That's the power. And what is happening, the pressure, after it catches it, makes it one-dimensional flow. The pressure on the outlet of the pump is greater than the pressure on the inlet of the pump. And pressure, when we covered Bernoulli's equation, we know that it's force per unit area, but you can also think of it as an energy per something, right? So if I put a distance here and a distance there, what is the force times a distance? That turns into an energy. And an area times a distance, volume. So pressure, very conveniently, is energy per unit volume. Very good concept to retain. So when you boosted the pressure outlet is greater than the pressure inlet, you boosted the energy content of the fluid. Now there's not 100% mechanical conversion of shaft power to fluid power, is there? So there's often efficiency of the pump due to viscous dissipation. We're going to repeat that. Here it is. So let's do this. Let's try and get our major components and our major efficiencies in line. We have a motor. A motor is an electric motor, and so it's taking in the plus and the minus electric wires. And if somebody said, I want you to calculate the power supplied to that black box due to the electric power, you would say, well, I'm going to have to know the voltage, the EMF, between the two wires that are supplying it. I'm going to need to know the current flowing in one of the, through, if it's coming in, it's also going out. This is a steady state, so I in is equal to I out. And if it's a DC type of system where it's not alternating current, then it's just the power, the W dot electric supplied to that motor is E times I. Very basic. Somebody says it's alternating current. Okay, what you can have is a PF. This is kind of stressing you a little bit, but what's the PF indicate for alternating current supplying to an induction motor? It's the difference between the sinusoidal voltage and the sinusoidal current. They're not in phase. When they're not in phase because of some inductance to the motor, because that's what a motor is it's an inductance motor. It's a bit like a big inductor. Remember you had capacitor, resistor, inductor. You said, why are we studying these things? Well, because electric motors basically are big inductors. Then you get the shift, and so the voltage, instantaneous voltage, is out of phase from the instantaneous current. And so to fix that, you put a power factor which has a maximum of 100%. What would be the maximum? When the voltage and the current are precisely in phase, back to like actually an like a DC. There's this, you don't have to worry about the power factor on direct current. It's the power factor is an alternating current. So a lot of times you'll see an equation that has a power factor in there. The maximum value of the power factor is 1. What's it due to? The voltage and the current are out of phase slightly. If you get good at working in energy and power, and you work for a company and they say, we want you to minimize our electricity bill, the electric bill, right? You're a big company and you're going to minimize their electric bill. You might want to look at two things. One of them is peak demand. That's usually about 30% of the electric bill. But also, you may look for a penalty if you're a commercial user of electricity, that the electric provider like CPS Energy penalizes you and makes you pay a higher rate because your facility has a bad power factor for the facility. You have a lot of induction motors. And what you can do is you can correct that by adding some capacitance into the system. But the electric utility provider does not like it when your facility has a low power factor. So anyway, there's the power factor. And then what is another factor that you'll see if you have three-phase power instead of single-phase power? because you have 3 lines for 3-phase power. Commercially, everything's pretty much 3-phase power. But in residential, it's not. But what are they talking about, 3-phase power? Well, you have 3 legs, 3 wires, they're hot, and they're out of phase with each other. And you just think of the whole circle. So you have take 360, right? Put one leg this way, another over here, and another over here. So how many degrees? 120 degrees, 120 degrees, 120 degrees. And so it's shifted. So if you wanted to put it on a time like this was coming up and then down. And so now that's, how many degrees is that in time? 360 degrees. So shift 120, I'm not going to do this very well. The next leg is coming up. And then the next leg is coming up. Like that. And so you have leg 1, leg 2, leg 3. Leg 1, leg 2, leg 3. And you'll have another factor right here for adjustment because you have the voltage, you have the current. Usually it's well balanced, so one line's current is the same as all the other lines' current. And then you have, I think it's what, square root of 3? Looks like it's the square root of 3, 1.7 something. Yeah, 1.73. Okay, so now we have a better understanding of the electric power that comes in. What comes out is the shaft power. This one's a lot easier. We've done it a number of times. If you could tell me the torque in that shaft and the rotational speed in that shaft, I could tell you the mechanical power that's being transmitted in that shaft, true? So what is W dot mechanical? Well, the torque for the shaft times the rotational speed. Do you agree or not? Now the question is the electric power supplied to the motor equal to the shaft power coming out of the motor? No, there's going to be a loss. And so we have the efficiency of the motor, and that's the W dot shaft divided by W dot electric. So it could be 93%, 98%. Luckily, there's a lot of very good electric motors out there. Even the old ones are still pretty good. The new ones are even better. So it's not uncommon to have in the high 90s the efficiency of electric motor. And a lot of times people will spend a little bit more for high efficiency electric motors, especially if they know it's going to go in there and last a long time. They don't want to touch it for 20 years, and yet it's going to be burning up and chewing up continually 50 horsepower, of electric power and putting out shaft power. So they would pay more for high efficiency. But then we run it into this pump. The pump takes the fluid, and the fluid goes out. And so we have another power. It's the fluid power, the mechanical fluid power. It's what gets into the fluid. Well, we talked about the pressure change of the fluid. And we can think of the pressure as the energy per unit. I forgot. Energy per unit volume. So we can think about the W dot that gets into the fluid. It affects the change in the energy content of the fluid, the mechanical energy content. Isolate that from making the fluid a little warmer like an egg beater would. Don't worry about that. That's not a useful form of the energy of the fluid if it comes out a little warmer. Okay? It's increase in the mechanical fluid power. So what would be a good equation for that? It would be the change in the pressure times the volumetric flow rate. Wouldn't that be it? Q, volumetric flow rate. Somebody says, if I take the change in the pressure divided by rho, and then I put rho times Q, isn't rho times Q mass flow rate? Sure. And then if I wanted to, I could also put change in pressure divided by rho G times GM dot. What is GM dot? This is volume flow rate. This is mass flow rate. This is volume. This is mass. What is G m dot? Okay, let's go back and do a quick. What is G? 9.81. 9.81 meters per second squared. Also, another favorite version of G is 9.81. Is this true? Is G 9.81 Newton per kilogram? It's probably the more helpful and useful form, but they never teach it. But if you could remember and know how to use it, because what did you just do? What is G? It's Newton, it's weight per mass kilogram, weight per mass, times the mass flow rate gives you a weight flow rate. It's a weight flow rate. So anyway, you can express this fluid power as either using a volumetric flow rate, mass flow rate, weight flow rate, just like we had 3 versions of Bernoulli's equation. So, but all of that shaft power doesn't get converted into fluid power, does it? So we have the efficiency of the pump, and that efficiency is W dot fluid, however which way you want to calculate it, divided by W dot shaft. So we have these stacking of efficiencies. Ready to go on? So let's talk about the typical centrifugal pump. Think about that radial flow pump where you have a nice eye, the water turns 90 degrees, gets into the impeller section and spits it out. Well, we plot on the x-axis when we talk about the performance of these pumps is we plot the flow rate. What do you mean the flow rate? Well, it's the flow rate of fluid through the pump. How do you measure it? You could use a cap Q. If you put cap Q, what's the units in SI for the flow rate? What units for cap Q would be? Meters cubed per second, right? And so it could go from 0, no flow, to very high flow rate. Or if you're working in USCS, and you'll see a lot of that still, what would be the typical flow rate for water pumps? Gallons per minute, GPM. Q would be in GPM, gallons per minute. Okay, so sometimes they'll have 2 axes. It's like a bilingual translation, right? You want it in Spanish, you want it in English, here it is. You want it in French, you want it in English, here it is. So they'll have another axis, and they'll have it, one will be cubic meters per second, 1 gallons per minute. Okay. Then on the other axis, they put the head. What symbol do they use for head? Oh, H or cap H or sometimes even P. Because the head can be represented in SI units in either meter, or it can be represented in Pascal or kilopascal or bar, something like that, some pressure. Or help me with the middle one. See this one and this one? Elevation, pressure. What's the middle one? This is energy per unit weight, energy per unit volume. What's the middle one? Energy per unit mass. You could put it in a number of different units, but something like, I don't know, joules per kilogram, kilojoules per kilogram. I try to put a different symbol, but the book doesn't do it, to distinguish between energy head, mass head, and the pressure head. But hey, let it go. So this is the head. What does it start with? 0. What's it go up to? Well, some maximum value. What exactly is it measuring? Well, I have a pump, and I have some change that happens between the inlet and outlet. Often it's easiest to think about pressure change. So what happened is I have a change in the energy per unit volume from inlet to outlet. That's the head. That's the head. Okay. So the performance curve starts maybe up here at this point right here. What did they do to get that point right there? Well, they took a pump and they let it not run dry, so they're going to feed it from large tank or a supply of water. It'll never run dry. It's going to get all the water it wants. And they start the pump up, and they have an outlet valve right there. And to get this first point right here, what is the flow through the pump at that first point? 0. What did they have to do to that valve to get no flow through the pump? They completely closed the valve. The valve is completely closed. This is not the way you want to run a pump, but it's the way you want to test and benchmark a pump and then report the data to it. And guess what the pump's going to do? It's going to fight and push, and it's going to produce a very high pressure change in the water from inlet to outlet, but there'll be no flow. It's a deadhead, 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 you know, and it'll have a very high head generated across it. Then they open the valve a little bit, and somehow they measure the flow rate. Maybe the flow rate's right here. Well, the head is a little bit lower. Then they open the valve some more, and they have the head a little lower. But the flow rate's higher. And then they have a sequence of curves, and it does something like this. How did they get those? Experimentally measure them. You could also predict them, but experimentally measure them. And then what about the other extreme? Let's say this extreme point right here. How did they get that point? Well, let's take a look at what about the head at that point? What about the pressure change across the pump at that point? 0. It's as if you just got rid of the valve and you just let this thing spit out with no restriction at all, right? And I know that you can change the elevation of this tank. Conceptually, that may give us a little trouble, but let's just say that the elevation of the tank and the water level in the tank such that this inlet pressure matches perfectly the outlet pressure. And what is the pressure gain then across the pump? 0. And so this point would be the maximum flow possible through the pump, but the pump kind of isn't adding any pressure to it. It's just kind of grabbing it from one end and throwing it out the other end. And this is the free flow. Yeah. Free flow. Okay? So that's the maximum. So all these other points are in, the measurements by conceptually closing the valve. So somebody says, I'm running at this point right here. I could get the flow and the head at that point, that operating point. All right. Well, let's do this. What is the W dot fluid? What is the power that gets into the fluid? Let's say at this dead point right there. Wouldn't it be the product of the head change across the pump times the flow rate? Isn't that the equation we just had? So we have, let's do it by, I'll do it with cap H, energy per unit mass, times the mass flow rate. Or let's do it this way. The change in the pressure times the volumetric flow rate. Well, what is the fluid power at that first point? 0. That seems funny, but you're adding no power to the fluid. You may make it warm, but no mechanical flow energy. What about this other point right here? What is, at the free flow, what is W dot fluid? It's 0 also, but why? No change in the pressure. Large Q, but change. So as I start moving to the interior at these points, these points, these points, what's going to go up is the fluid power is going to go up. And often the fluid power, the way they have the shape is the way I've shown it. is a maximum somewhere in there, meaning the maximum power got into the fluid. Okay. Well, for each one of these test conditions, they could be measuring also W dot shaft going into the pump. If they measured the shaft power going into the pump, they could then get the efficiency. So they could get the pump efficiency. The efficiency of the pump would be W dot fluid divided by W dot shaft. What is the efficiency at this point over here, this deadhead point? 0. What's the efficiency down here? 0. And so essentially the efficiency is normalized, fluid power is going to be increasing, and then you'll get to some point in here. And at one point in particular, you'll get to a point where along that curve for that pump, you have the BEP, the best efficiency point. So where would you like to operate that pump? You would actually like to operate it in the vicinity of the BEP. This is the best place to operate, where you want to operate the pump. Okay. So this is a sequence of data points called the curve. It goes from the shut-off head or the dead head to the free capacity. You have at the extreme ends, you don't want to operate there. The efficiency of the pump is 0. You only want to operate out in this sweet spot, depending how rigorous you are, how close you want to get to the best efficiency point. But it would be great to operate right at the best efficiency point for that pump. That's the pump curve. Now let's take a look at our illustration out of the textbook. And so we have the shut-off head. First of all, they have a couple y-axes. The x-axis is just the volumetric flow rate. You have the y-axis, you can have that head. Sometimes they'll have another axis over here. It'll be the efficiency of the pump. And sometimes they'll have another axis, but rarely do they have an axis for the brake horsepower, and that's W dot shaft. It's the shaft power needing to be supplied to the pump, the brake horsepower. But let's take a look. What is this one right here? This is our head versus flow rate. That's our system curve. What is the efficiency of the pump at this point? The efficiency of the pump is 0. What's the efficiency pump at the free delivery at that point? 0. And so if you plotted the efficiency of the pump, it goes up and it goes back down, and somewhere it gets to the maximum efficiency. This would be that operating point at maximum efficiency. They put an asterisk on it for the optimal, the best efficiency point. How about the brake horsepower? Maybe they put a plot over here. The brake horsepower as a function of the flow rate for this pump. It's goes up as a shape like that, goes down a little bit, and right in here you get the brake horsepower at the best efficiency point. So there's a lot of information on these pump performance plots. Let's take a look at a real one. This is from a supplier, Taco. I'm not certain exactly how to pronounce that, but what do they have down here? They have flow in gallons per minute from 0 up to 1,000 GPM. That's a lot of flow. They have the head in feet from 10, 20, 30, all the way up to 70. They have a particular model number of their pump. It's running at a particular constant speed at 1160 RPM. They have some numbers here, which we can get into later. Often these numbers, this one's a 5 by 6 by 11. What is that, a quarter? The first number is the diameter of the discharge, then the diameter of the suction. These are the two diameters, and this is your impeller diameter, the maximum impeller diameter in that model number right there. So let's take a look here and find a system curve. This is for the maximum impeller diameter that fits in that casing, that curve right there. Often they don't take it all the way down because they don't want you to operate down there, and nobody really wants to operate down there either. But they will take it further back because sometimes you do deadhead the pump. You shut a valve off in the system and the pump's just pushing hard against a pretty closed valve. And so what is this number right here? Can you read that? 11.30? That's essentially the 11 and 0.25. That's the same number. That's a maximum impeller diameter. So for that maximum impeller diameter running at this speed for this model, if you wanted to push 500 GPM, it would be giving up around 53 foot of head. That's how much pressure gain across that pump would be at that flow rate. Okay. What about these other curves? This is for a different impeller diameter. Which diameter is that? 10 inches. You can actually take the same casing and put in an impeller that's really snug or an impeller that's not so snug, and it'll work. So what do they have here? If you had that different impeller at 500 GPM, it would be 40 foot head gain across the pump. So that's why they have, in this case, how many different pump curves do they have? It depends on the diameter of the impeller. 1, 2, 3, 4, 5. They don't recommend going any smaller than this diameter, nor it wouldn't fit anything larger. Now, what do they have for these lines right in here? What are they showing us? What are these lines showing us? What does this number look like? They're percentages. So what's this highest number right in here? 84? That around 84? That's the efficiency of the pump. How well does it convert the mechanical shaft power into fluid power? So let's say I was operating at this 500 right up here. What would be the efficiency? Somewhere between 82 and 83. It looks like it'd be maybe, just call it 82%. You know, you want to be a little shy on the estimate. Or if I was operating at 200 GPM with the 11-inch impeller and it was right there, what would be the efficiency close to? Around 60% efficiency. Okay? So all these curves are showing you the different efficiency. Well, along each of these performance curves, you have one point that has the best efficiency point. That would be the point right there for that one, there for that one, looks like there for that one, there for that one, and there for that one. That's the best efficiency points for each of these. Okay. Okay. The curves are based on water with a specific gravity of 1.0, so it's just pure water. What do they have right here? What is this dashed line? I'll try and highlight it. It goes right there. It didn't go very far. Here's another dashed line. It goes right there. And here's another dashed line. It goes right there. What are they showing us by those dashed lines? Yeah, it's the BHP. So what is BHP? Brake horsepower. So the shaft that's coming to that pump, if you're operating it along that line, needs to be 5 horsepower Along this line, 7.5 brake horsepower. Along this line, 10 brake horsepower. It's telling you how big a motor needs to be on that pump. So right at 500, right here, if I came up to this point right here with 50, it looks like I need a 7.5 horsepower motor. What would happen if I put a 10 horsepower motor on it and it was operating at 550? So I'm operating at this point right there, 500 GPM, 50 foot ahead. I'm with this 11-inch impeller diameter. I'm running at 1160 RPM. It says it needs 7.5 horsepower, but I actually have a 10 horsepower electric motor driving it. And then I say, no, I need 7.5 horsepower, but I actually have a 5 horsepower motor driving it. Do both cases. Which one's good? Which one's better than the other? The 10, right? Which one would lead to a catastrophic result? The 5. So what will happen with the 10 horsepower motor? It's like no sweat. It doesn't even break a sweat. It just sits there and runs. And actually, it'll drift up a little bit because this is a slip speed. It'll drift up. Maybe it'll actually run at 1170 or 1175 RPM. It'll run just slightly faster than that 1160. The synchronous speed is, you can tell they go in increments, it's 1200. But this will really supply the necessary shaft power to make the fluid system work. It'll actually supply the 7.5 horsepower, meaning it has excess of 2.5 horsepower. Okay, it's capable of producing more power. What about the 5 horsepower motor if you put it on there? Well, it would try really hard to do the job. And its speed would actually fall. It would fall below the 1160. And what would happen is you would get a greater separation between the current and the voltage in that induction motor. The current in the windings would go up. Anytime you have high current in any wire, you will get more resistive losses. It'll show up as heat, and the motor will get hotter. And then each of the electric motor windings have a little coating to them. If you ever take a look at the motor wires, the little electric insulating coating and the wires lay touching each other. And the current's supposed to flow through the wire, not jump from side to side to the next wire. But when the coating gets hot, its insulating capability goes down. You get a short circuit. Now the electricity even goes up higher because it doesn't have to go so far. The current goes up higher, and now you even get more heat dissipation, and it doesn't take long to burn out a motor. And if anybody's ever smelled any electronics where it burns out, it's nasty smelling. So this is no good. So a lot of times what an engineer will do is they'll over-specify the motor. It's safer, and that'll be that. It just costs more to install it. Let's play some games. This pump, is it a good match to operate at 500 GPM with a capacity of 40 foot head, yes or no? 500, come up, 40 foot. What do you think? Yes or no? Which one is it? Would this pump be okay? Actually, it'd be good with a 10-inch impeller, wouldn't it? Okay. How about this one? Would this pump with any of the impellers at 500 GPM at 65 foot? Here's 500 GPM, come up to 65 foot. With any of those impellers, would this pump be a good selection? No, it would not be. How about at 200 GPM and 20 foot? Would any of these? No, it would not be a good selection. No. And how about 700 GPM at 35 foot? 35, come up to here, right there, 735. It would be okay, but I would like it to be near the middle. Okay, I would like it to be because this one, what'll happen is I'm going to have to either get a larger motor, a larger impeller, and then if I really want it to run at 700 GPM, I'm going to have to put a valve in there and close it a little bit. And the head will go up and the flow rates, so it's, anyway, that's what would happen there. I would add a little valve and close it a little bit. So it's okay, but not optimal. You want to stay in the range of the best efficiency points. A lot of manufacturers put out a bunch of composite maps, or even they have them in the computer codes. So you figure out sort of the flow you need. Oh, I'm in this range for flow. And the head that pump has to generate to make the loop. And maybe it's right here in this range. And you come over and they overlap another of them, but you can take a look and think about below. And they have these little composite maps, and it'll show you where to go, which pump. Don't try this pump out here. It's not the right pump. You need a pump that works in that vicinity. Okay. A pump increases the head of water with, from 10.2 meters to 306 meters at a flow rate of 1 meter cubed per minute. The inlet and outlet pipe diameters are the same, and there is negligible change in elevation across the pipe. Across the pump. The pump efficiency is 77%. Determine the shaft power supplied to the pump. So there's our shaft. W dot shaft goes to a pump. The pump takes in fluid. Maybe I'm drawing this all wrong. Here, take the fluid, discharge the fluid, and you supply W dot shaft. Okay. So determine that shaft power needed. How are you going to calculate that shaft power needed to drive this pump? Well, how about in the interest of time I pick it up? So, okay, if you take the shaft power multiplied by the efficiency of the pump, you get the fluid power. True? And so if you're trying to calculate the shaft power, probably the best thing to do is calculate the fluid power, then divide by the efficiency of the pump, because efficiency of the pump was 77%. Okay, so I would bust it into two steps, getting first the fluid power. What actually is the mechanical energy that got into that fluid? Well, there's three great equations. You can multiply the change in pressure across the pump times the volumetric flow rate, or the change in the energy per unit mass times the mass flow rate, or the change in the elevation head times the weight flow rate. I don't have a separate symbol for the weight flow rate, GM dot. Or you could say, let's take a look at what's given to us. So we have the change in the elevation head, that's 306 minus 10.1 or 10.2 meters. So that's the change in the elevation head. You're given a volumetric flow rate of 1.0 meter cubed per 60 seconds or per minute. It's water, so the density of water is 1,000 kilograms per cubic meter. And we know what G is, 9.81 newtons per kilogram. So the fluid power is 306 minus 10.2 meter elevation change times 9.81 newtons per kilogram for G, times the density, 1,000 kilograms per cubic meter, times the volumetric flow rate, 1.0 meters cubed per 60 seconds. And the meters cubed go, the kilograms go. I'll get a Newton meter per second. Newton meter is a joule, and a watt is a joule per second. And I probably want to get rid of a kilo is 1,000. And so get rid of this 1,000 with the kilo. And I'm going to have the final answer in kilowatts for the fluid power. How many people were able to get W.F? What is that for the fluid power in kilowatts? And then I come up here and I have the 48.4 kilowatts, and I divide it by 0.77. And so W dot shaft is 62.8 kilowatts. Good? All right. Press forward. Cavitation is a real issue. What is cavitation in water pumps or rotating machinery where water is there, or any liquid? It can have cavitation in any liquid. Well, cavitation, rapid formation and collapse of vapor pockets or bubbles or voids in a flowing liquid in regions of very low pressure. The low pressure are often caused by rotating machinery, but actually you can have rapid flow through a device, and the device walls are stationary. They're not rotating or anything, and you can have cavitation. It's just where you have liquid flow and somehow you have an extremely low pressure region. And in that very low pressure region, vapors want to form. They'll form in bubbles. And then the flow continues to sweep. Well, it was at high pressure, goes to low pressure, then it goes sweeps the fluid packets with those bubbles into a higher pressure. Bubbles no longer are in equilibrium, and they collapse. And when they collapse, the way they collapse is complicated, but you can get a little high pressure pulse. And if it collapses near a wall or something, that pressure pulse, pushing and pulling like that pressure bang, could actually erode the material. And so cavitation is formed of vapor cavities in a liquid, and these are bubbles or voids, and they can cause a lot of damage. So to understand cavitation, we need to go back to Thermo 1. We need to go back to our pressure temperature diagram, and you could do it for water. If you understand water, you can do it for any other liquids as well, or any other substances. And I know that in general we have the solid, we have the liquid, we have the gas region or vapor region. Let's call this V for vapor. But we're really only focused on this area right out in here, where we have liquids, and then it can change into a gas or a vapor. It's the same substance, it's just in whatever state it's at. And so on this pressure temperature diagram, we could start with a point. Let's say the point is right here. It's at this pressure and this temperature. It's in, what would we call that from Thermo 1? It's in the subcooled liquid region. It's not near being saturated liquid. It's not near the point of changing phase. How could you get this liquid at that point? How could you get this liquid to change phase? Maybe you think back and you put it in our piston cylinder assembly, right? And we have this substance right in here, and it's completely liquid. And somebody says, I want you to change that to a vapor. What are you going to do to accomplish that? Okay, there's two things you can do. You typically can go along this line or along that line, and we need to understand both. So if somebody says, I want you to go along path A, the horizontal path, to get it to where it's going to change pressure, change from liquid to vapor, and then if you continued on that one, it would get out here into the superheated vapor region. What would be happening along path A? What would you be doing? You would be trying to boost its temperature without changing the pressure. So in our piston cylinder, we would keep a constant weight piston. The weight of the piston is constant. Frictionless cylinder, so it's sealed, but it's frictionless. And what would we do? We would heat it. And if you heated it, what would happen to the temperature of the water? It would go up. And it would stay at that pressure. And then you would see dramatic rise in that piston. Its weight didn't change, so the pressure doesn't change. Because of the expansion from liquid to vapor, it's constant. But what was the key? Increasing the temperature. How would you increase the temperature? Until you got to the saturation temperature, you would increase it by heating. Now, let's do the other one. Let's go along path B. How do you go? What's going to happen in this case? The pressure is changing, but what about the temperature? Along B, does the temperature change? No. So what happens, maybe you put a rod on here and you're able to exert a force and you're going to lift it. What's happening is I try to pull up on that piston, additional force, it drops the pressure. And I know that you're thinking, hey, isn't that a little bit of boundary work? Couldn't that have an effect on the energy balance? But let's say the boundary work is so negligible that the temperature, the internal energy doesn't change. It stays constant. All I'm doing is pulling up. Could I pull up to the point at which it gets to a different saturation temperature? Basically, I'm decreasing the pressure until I get to the saturation temperature. At that point, if I pull up, what's going to happen? I'm going to get some little vapor bubbles forming, little voids in there. Now, describe to me, does it take energy to change from a liquid to a vapor? Does it take energy? And why does it take energy to change from a liquid to a vapor? Because you're breaking some sort of bonds, not molecular bonds, but intermolecular bonds, bonds between the molecules of the liquids that are attached to each other. It's not a very strong bond, but it's a bond nonetheless, and you have to break those to turn it into vapor. True? Okay, so as we heat it, you're adding more energy. It's able to overcome and turn it into vapor. And this would be HFG. Wouldn't that the heat of vaporization at that saturation temperature? Isn't that quite a bit of energy often? A lot, right? Remember some values of HFG for water at 1 atm? Over 2,000 kilojoules per kilogram. But what about down here? If you're forming bubbles, not by increasing the temperature and heating it, but you're just decreasing the pressure and pulling up. Do you still have to break liquid intermolecular bonds? Okay, where's that energy going to come from? It's not coming from a heat source. Let me ask this. I know that this is at a slightly different temperature, this case and that case, but is HFG for both of those cases approximately the same? Yeah, they're approximately the same. Let's say they round them off to 2,000 kilojoules per kilogram. Do I still need to supply 2,000 kilojoules per kilogram if I'm just decreasing the pressure? Where is that 2,000 kilojoules per kilogram for water going to come from? Mechanical energy? Well, you might want to do a quick check on that one to see what it would be. Where else could it come from? Well, let me do this. I think I've laid out the path A of heating and the path B of decreasing pressure. We've we realize that changing from liquid to vapor can occur by both of those, and both of them have to break those intermolecular bonds. That energy is going to have to come from somewhere. Let's do this. Let's contrast the term boiling from your experience with evaporation. It's very similar, isn't it? So think of an example of boiling. I put a pot of water on the stove, and then I heat it up from the bottom. What's a good example of evaporation of water? Well, take water after it rains. Maybe I have a street, a driveway, something. I see a puddle out there. It's sitting out there, and after a couple hours, what happens to the puddle of water? It's gone. True? That's a good example of evaporation. So we have a pot of water as an example of boiling, and a puddle of water on a street or driveway or cement sidewalk as an example of evaporation. Do we have liquid changing phase to vapor in both of these cases? Yeah. Where is the boiling occurring for the pot of water on the stove? If I have my pot right here, where does the water change to the vapor? I know that if I blow some air across it, that it'll be taking, and some will happen right here, but a lot of times, if it's really boiling, I have little bubbles form on the bottom. They come up, they're detached from the top, and they sort of pop out the top of the pot of boiling water. You ever see it? So it's like popping out. It's like a steam kettle. If I had a kettle here on it and I had the control, it would just be issuing a vapor stream. True? Not an open pot, but maybe a steam kettle. I know that at the beginning there'd be some air in there, but that would naturally get swept out. And after a while, after boiling for a while, the only thing up in here would be H2O vapor. And all of this would be the liquid, and all the air would have been gone out, and you're still issuing a stream of little... anybody have a teapot? You ever see that? My wife likes it. And the little whistle goes, you know it's done, right? No sense in boiling any more water. It's hot as it's going to get. All right. So where does the vapor, liquid, turn to vapor in this pot? Definitely at the bottom, at the solid interface, the solid-liquid interface. Where does, in the puddle, where does the liquid turn to vapor? Do I have, here's my puddle, here's my concrete, and there's the air blowing over it. Isn't it occurring at the interface of the liquid gas, air drying, going across the top and drying it? Yeah. So it's a difference of where the bubbles occur or where the liquid changes to the vapor. What happens? We have bubbles. They're little packets of vapor. They're formed below, and they rise in liquid and pop out the top. Are there any bubbles in evaporation? No. There's no bubbles in evaporation. The bubbles escape the liquid into pure vapor, or if you had an open pot, it could escape into an air mixture. It's easier to think about it, bubbles going into pure vapor. Here, when you have evaporation, where does the water vapor go to? Does it go to pure water vapor? Probably not. It goes to air. This is the air. Boiling can be fast, and it's really controlled by the heat transfer. If I take that pot off of the hot burner and set it to the side, does it continue to boil, or does it stop right away? It stops right away. There's very, very little thermal heat in the bottom of the pan of water. It's not like that solid bottom of the pan of water is very, very hot, higher than the saturation temperature. As soon as you take it from the heat source, that teapot quits whistling. Okay. But over here, it's slow, and it's not controlled by the heat transfer as much as it's controlled by the conditions of the air. How dry and how warm the air is compared to the water. So the solid surface temperature is above the boiling point of the water, and that's what dries it. So you get the temperature of the surface greater than Tsat, and then if you make it a lot greater, you can get go from just little nucleate boiling all the way to film boiling, the large vapor blanket covering the surface. You don't see that often. But here, air temperature is, with the water, is below the boiling point. The air temperature to cause evaporation does not need to be to the magnitude of the saturation temperature. But you have to have the surface temperature greater for boiling. So these are kind of key points contrasting the two. We have heat transfer from the solid to the liquid. You still need a heat transfer to break those intermolecular bonds for evaporation. But where does the heat transfer come from? It can come from two places. It can come from within the liquid or from without. You can think of this as evaporative cooling. How many people sweat? Why does your body sweat? It sweats so you can reject heat. How is it helping you reject heat by sweating? By evaporatively cooling your sweat. That's what it does. So a lot of times people, oh, I'm hot, you'll jump into the pool, you'll get out of the pool, your t-shirt or something else will be all wet, your clothes will be wet, and you'll feel cooler in the same breeze at the same temperature because it's evaporatively cooling you. Okay, a lot of examples of evaporative cooling. Okay, if I actually took and put this in a very, 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 very well insulated container, and I put a thermometer in there, and I didn't blow air over it, but then I started to blow air over it, there could be a reduction in the temperature of that liquid. Yes. It would be trying to break those intermolecular bonds to generate vapor, and it would reduce the temperature of the liquid some. That's coming from within. From without, well, maybe this air is warm, and now the liquid is cool. You actually have convection heat transfer, and that'll help promote evaporation because the heat transfer is coming from some warm sun. Maybe it's in the direct sunlight. That's adding some photons, it's adding some heat. Boom, and that's a heat source. A little more complicated here. But boiling, you can sometimes even hear the boiling. You ever have a pot of water and you can hear that click, 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 something like that? That's a vapor pockets coming up and then collapsing, especially when they don't start to get to that churning state in the boiling. Those little noise bubbles. It's fast, it's loud. Evaporation, you ever go out and listen to a puddle evaporate? Hey, quiet out there, the puddles are evaporating, breaking up, the neighborhood, peace in the neighborhood. No. But you often, this is loud. You can hear the clicking, the popping of those bubbles before you get the onset of that rolling boiling. So with that as a background for the cavitation, we know that to prevent cavitation in a pump, here's our pump, cavitation is going to occur when the pressure is the lowest. And where is the pressure the lowest? At the suction. And if I look at the suction line, I got a point A over here and a point right there at the inlet, at the very inlet to the suction. Which one is lower pressure? This point right here, point A or point B? It's always going to be B because the flow is going that way. Friction creates the lowest pressure in the direction of flow, and then boom, so that's the point where you have the lowest pressure, and you have the highest probability of having the problems with cavitation inside the pump. So now once you get inside, there's rotating machines, blades and impellers, and the pressure is changing from within the pump, but from a black box perspective of the pump, that the very inlet to the pump is the lowest pressure. And so they'll define the net positive suction head is defined as the stagnation pressure minus the saturation pressure of the fluid for that temperature. Okay, well, if you hadn't taken this class, you would be confounded by what do they mean by stagnation pressure. But so far in this class, we've talked about stagnation pressure. We've talked about it in the context of a little tube that we insert into a flowing fluid to measure the speed of the flowing fluid. What was that little tube, the name of that tube? That tube that comes up and shaped like this in the flowing fluid? Pedostatic tube, right. Okay, you can have just a pedo or a pedostatic tube, but often it's a pedostatic tube. And what about the flow right at that tip, at the tip of that pedostatic tube? It's the stagnation pressure. And so what is the stagnation pressure? It's the static pressure plus the dynamic pressure or the velocity pressure. So what is the static pressure? Well, it's probably best to think back to this pump system. If I take and I put a pressure gauge right there, I put a tap into it, into the pipe right at the inlet to the suction line of the pipe, and I come up here and I put a pressure gauge right there, what's that going to measure? It's going to measure the static pressure. But then I have to add this dynamic pressure. What is the dynamic pressure for flow? That's right. So the pressure, the normal pressure, our static pressure, something you would measure with a pressure gauge, plus the 1/2 rho v squared, that's our stagnation pressure. Then you subtract off the saturation pressure. What is the saturation pressure? Well, that's a function of temperature. If we go back to this plot right here, this line curve right there, for this temperature, there's my saturation pressure. For this temperature, there's my saturation pressure. For this temperature, there's my saturation pressure. And so let's say for water, what is Psat at the temperature of 100 degrees C? What's the saturation pressure for water at 100 degrees C? 1 atmosphere. 14.7 psi, 101.3 kilopascal, somewhere around there. And as you go lower temperature, it's a lot less. So this is the definition of the net positive suction head. You almost have to just think about this and try to memorize it, but it can be confusing at times, but if you go slow, it's the stagnation pressure, the combination of static and dynamic pressure, but you have to subtract off that saturation pressure. Well, to avoid cavitation, the pump manufacturers will often report what is the net positive suction head required to avoid cavitation. And they can give it in a bunch of units. They can give it in meters. They can give it in kilojoules per kilogram, or they can give it in Pascal or something like that, kilopascal. What are they doing here? It's just like what we've done all semester. You can talk about the energy per unit weight, energy per unit mass, energy per unit volume, energy per unit weight, energy per unit mass, energy per unit volume. What's the most common? This one, meters. But sometimes they'll put it in Pascal, very rarely energy per unit mass. But that's the net positive suction head required. So the net positive suction head required may be, I don't know, 14 meters. That you have to make sure that the suction inlet condition is above that, or you're going to have problems. So to avoid cavitation, you need the net positive suction head available needs to be greater than or equal to the net positive suction head required. So if 20 is what's available, you compare it to what's required, 14, you're okay, you're going to avoid cavitation. If it's 5 meters and you compare it with the 14 meters, it's not okay, and you're most definitely going to have problems with cavitation. All right. So We had the general definition of the net positive suction head. What was it? The stagnation pressure minus the saturation pressure. And then we talked about having what's required and then what's available. So there's really three things you need to keep straight. What is the definition? The pump manufacturer says this is what's required. And then you have to say for that condition with this system, it's what's available. Let's do this problem. Water at 30 kilopascal and 60 degrees C. So what do they tell us by this information, 30 kilopascal? Is that the stagnation pressure or the static pressure? Static. It's 30 kilopascal. And the temperature is 60 degrees C. Enters a pump in a 25 centimeter diameter pipe. So the diameter of the inlet's 25 centimeters. At a flow rate of 0.15 meter cube per second. To calculate the net positive suction head available at the pump inlet. So the emphasis on available. What's available? So net positive suction head available is going to be the pressure static plus 1/2 rho V squared minus P sat at 60 degrees C. So we take a look. What is the pressure, the saturation pressure at 60 degrees C? It's 19.94 kilopascal. You have to go to the tables or other source to get that. And the static pressure was 30 kilopascal. And what about this dynamic pressure? Well, I have to get the speed. How do I calculate the speed? Isn't that the volumetric flow rate divided by the cross-sectional area? Volumetric flow rate divided by pi d squared over 4. And when you calculate the speed, you get it 3.055 meters per second. Then I can come up here and I can calculate that it's 1/1,000 kilograms per meter cubed times 3.055 meters per second squared. How many kilopascal is this? Run your calculator for me, would you? We have 1,000 kilograms per cubic meter, 3.055 meters per second quantity squared. 4 point. Okay. Anybody else? You like it? We got a 2. Anybody else? So we have 30 plus 4.66 minus 19.94. All of that is kilopascal. So what is the net positive suction head available? $14.7? 14.7 kilopascal. Somebody says, I want the net positive suction head available in meters. How do I convert from kilopascal to meters? What's the meters? The meters of a water column or water gauge or something. It's head, elevation head. Can you do that? Divide by rho g. And so what do you get when you do that? 1.5 it is, in units of meter. So either you have the net positive suction head available in pressure or in elevation head. Either way works. Okay? Here's another pump, and it's an inline pump. They have different descriptions. Once you look at it, it makes sense. The fluid flow, and all you want to do is boost the pressure, and it's as if you could cut the pipe section and put it in, and it's an inline pump. You can see that the fluid here comes and flows into the eye, and then spins around and then goes out. That's the way it would work. And here's our performance characteristics: flow rate up to around 80 gallons per minute, head up to around 45 foot of head. This pump is to operate at 55 gallons and 30 foot head. So here's 55, here's 30. It looks like it crosses right about there. What is the size of the motor needed to run the pump? This one, they put the size of the motor right here, and so it needs a 3/4 horsepower motor, 3/4 horsepower motor. And what is the net positive suction head required to avoid problems with cavitation? Where did they tuck that information? Well, you have to look at these, and right there it is, and there's the information. So they're saying the net positive suction head in feet. Did they put an R on there? No, they just said this is what's required to avoid cavitation. And so since we're operating at this point right here, this is where the 7 kind of drops down. They stopped with the line that it would just be continued. Like this is 8, this is 9, and this is 10. So if I'm going with higher flow rates, I have to have a higher net positive suction head available, that the minimum is higher to avoid cavitation. So at this point, you can just see that, hey, I need 7 foot to avoid cavitation. So the answer is 7 feet. That's the net positive suction head required. It's a characteristic of your pump. Okay. Here's a big one. So this is a horizontal split case double suction pump. What happens is the fluid comes in, and to keep, it'll split the flow, and it'll some go on that side and that side into the eye region. And because of that balance, 50% coming in from the left, 50% from the right, you don't have a net thrust one way on the bearings. It's more, so you'll see a lot of split case double suction pumps. All right, so it's operating at 5,000 GPM. Here's 5,000, somewhere along this line, I believe. And 275 foot of head. That's around right there. Looks like right there is a good operating point. What size motor is required to run the pump? It looks like the motor, if I come in with, this is 450 horsepower. That'll work. So I'd say put at least the 450 horsepower on it. If I think that the operating condition may drift and somehow get out into this vicinity or this vicinity, then maybe I want a larger horsepower motor on there, 600 horsepower, okay? Okay. But now, what is the net positive suction head required? This one's a little different. They put the required curve, and not just straight line, but a curve right here. And then they tuck in its own independent coordinate system, you know, the y-axis over here. And so if I look up, it's at this point, and I have to read over, and it looks like I need to have about 25 foot, or you can get it in kilopascal as well, both in feet and kilopascal. Isn't that interesting, right? Feet is US, kilopascal, SI. Okay. Well, I didn't go as far as I wanted to today. I'll pick up there next time. Thank you for your attention. If you did not pick up the quiz that we had last time, it's graded and down here for you.